Welcome back to Chem 4300. In this video, we begin Chapter 14 on radiating dipoles in quantum mechanics. And it's here that we finally have an opportunity to solve the mystery of Ernest Rutherford's model of the atom. If you remember, back in 1911, Rutherford proposed a model of the atom that had electrons orbiting around a positively charged nucleus at the core of the atom. And he knew this idea was a little bit crazy because according to classical electricity and magnetism, any charged particle like this negatively charged electron, as it moves in an orbit like that, would radiate away its energy as electromagnetic waves, and it would collapse into the nucleus. Niels Bohr took this model and proposed for a further theory of the atom, and in his model, he said that electrons will remain in these orbits, but he intentionally gave no explanation for why the electrons do not irradiate away the energy of their orbital motion. Now, on the other hand, we know that atoms will absorb and emit light, and this was first noted by Fraunhofer when he measured the spectrum of the sun, and he saw those dark absorption lines which were associated with the elements that were in the sun. So whatever quantum mechanical treatment we put together, it has to allow for both of those possibilities. It has to allow for the stability of the atom for electrons to be in these orbitals and not radiate away their orbital energy. But at the same time, it has to allow for atoms and molecules to undergo transitions in these orbitals where they emit or absorb light. So what we're going to do in this chapter is we're going to look at the quantum mechanics for determining the rules for when atoms and molecules can and cannot absorb electromagnetic waves. And as we learned earlier, one of the simplest models for generating electromagnetic waves is an oscillating electric dipole, and it's a very strong source of electromagnetic waves. And so if we take our expression for the operator, take our expression for the electric dipole moment and turn it into an operator form here for some collection of charges, then we can use this to calculate the expectation value of an electric dipole moment and look at that time dependence. So what we're going to start with is just simply a charged particle, say an electron that's bound to a positively charged nucleus, and we're going to write down, in the simplest case, its electric dipole moment operator. Now, if I take that dipole moment operator and I calculate its expectation value, I just simply make this sandwich here where I have the complex conjugate, the operator, and then the wave function again, and I integrate it over all space, and I get the time dependence of my electric dipole moment operator. Now, with this case here, I'm going to put in my operator, and this is the integral I'm going to be doing. Now, don't forget that this d tau is just dx, dy, dz, and this is a volume integral over all space. Now, starting with that integral, let's calculate what this time dependence might look like. So we're going to start with the case where the electron is in an energy eigenstate of the Hamiltonian. So if you remember, that wave function has this form here, and it will have a spatial dependent part and a time dependence part that's just simply e to the minus I ENT over h bar, where E is the energy of that particular eigenstate. So if I take this energy eigenstate and I use it in my calculation of the electric dipole moment, then I have this expression here. And what you notice right away is that this complex conjugate of this wave function up here changes the sign of the exponent. So this e to the I ET over h bar is going to meet up with this e to the minus I ET over h bar, and they're going to cancel each other out. So what we end up with is this integral, which is just involving the spatial part of the stationary state or the energy eigenstate of the Hamiltonian. And if you look at that, you realize, wait a minute, there's no time dependence left. So this dipole moment operator's expectation value for this energy eigenstate has no time dependence. If it has no time dependence, then it's not going to be an oscillating dipole and give off electromagnetic waves. So no bound charged quantum particle in an energy eigenstate can radiate away its energy as light because there's no time dependence in its electric dipole moment, or at least it appears that way. And this, of course, is good news for Rutherford's atomic model because he can say that the electron in this orbit around the nucleus is in one of these energy eigenstates, and that's why it's not radiating. Okay? Well, then that leaves us with another question then. Well, we know that atoms will radiate their light and actually absorb and emit light. So how is it that a charged particle that's bound to some potential manages to do that, right? How can it radiate light and, say, for example, start from an excited state and fall down to this ground state? Well, the one way we can see how this can happen is that if we consider this transition in progress and look at the superposition of energy eigenstates that will be present when a transition is taking place. So if I have a transition from an energy eigenstate, say, labeled by M, to a lower state that's labeled by N, then during the transition, it's going to be a linear combination of this energy eigenstate and that energy eigenstate. So I'm going to write that in this form where A is some coefficient that determines the relative amount of these two energy eigenstates. Now, before we begin the transition, when we're in the excited energy eigenstate, then this coefficient, the AM coefficient, is going to be equal to 1, while the AN coefficient is going to be equal to 0. That means we're entirely up here in this excited energy eigenstate. But then after the transition is over, we expect to be down here where AN will be equal to 1, so for time equals infinity, and then AM, time equals infinity, will be equal to 0. So these two coefficients here have to be normalized, so the square of both of these coefficients added up have to be equal to 1. Now, if I take that sandwich for the expectation value for the electric dipole moment, and I plug in that superposition of two energy eigenstates, I'm going to write them out here. And what I'm doing is I'm putting the M states in blue and the N states in red, so we can sort of keep track of them a little bit easier here. And when I expand out this integral, I'm going to get 4 integrals. And you can look carefully to make sure that this is all done correctly here. But you see that there's going to be integrals involving just the M state, integrals involving just the N state, and then these cross terms which involve the M and the N state here and there. Okay? So we have 4 integrals that result in what gives us the expectation value for the electric dipole moment. So let's look at these more carefully. So this one involves just the M state. Well, we already saw that that one was a time-independent integral. So this integral itself has no time dependence. The only time dependence that it has is what's carried in these coefficients, the AM coefficients. And so this is a time scale that's slow in a sense that it's the time scale at which the transition is occurring. But there is a time dependence that's here in these coefficients, but nothing here in this integral. Same is true over here for the N state, N eigenstate. It has no time dependence in this integral, just a time dependence here in these coefficients, whereas these cross terms are going to be time dependent in the integral and time dependent in their coefficients. And it's this time dependence in the integral which is going to be the faster time dependence, which is going to be giving off the significant amount of light. Okay, so remember that the radiation that's emitted by a dipole goes with the frequency of the oscillation. So the faster the oscillation, then the more light that it's going to give off. The fast oscillation is in these terms. These guys have no oscillation. There's only a slower oscillation there. So we're going to drop these two terms because they really don't contribute much at all to the time dependence of the electric dipole moment. So we'll leave those terms off, and we'll focus only on these two terms here, which I've written here. Now, if you stare at those terms, you realize that they're actually complex conjugates of each other. If you take the complex conjugate of this, you'll see this. So if we go ahead and simplify this a little further, we can write down that this electric dipole moment, which has to be a real quantity, then it's just simply the real part of this single integral as written here. Okay. So these two are just complex constants of each other, so we can just write this result as just the real part there. So now we'll take this and let's dig a little deeper, because this is where our time dependence is going to come from. So with this expression, I'm going to substitute in my energy eigenstate in this form. And when I do that, plugging in here and here, well, again, because I'm taking the complex conjugate, there's a missing I there, sorry about that. When I take the complex conjugate, there's a sign change. So when the time-dependent part from the energy term here shows up in this integral with the complex conjugate in the original one, it shows up here as the difference between the energies. So we have e to the I, Em minus En, where this is the excited state and this is the lower energy eigenstate. We also have this term here, which is the expectation value for the electric dipole moment evaluated with the spatial part of the wave function. And then we have that earlier term here, which is just the A's, which tell us about the time dependence of the transition. So this term here, this is the fast oscillating term, and that's going to have a frequency, be associated with the frequency of omega, which is the difference of those energies divided by h bar. That will be the frequency of the light that's emitted from this oscillating dipole. This term right here is going to give us the magnitude of that dipole oscillation. And so this is something that's called the transition dipole moment. And we'll be coming back to this a lot in this chapter and later in the class. And then, so finally, we will write this whole thing down like this, where we have it now in terms of the time dependence of the transition contained here. We have the sort of how long it takes for the transition to take place, the size of that oscillating dipole moment, and then the frequency of that oscillating dipole in terms of the light that it's going to be giving off. So just to summarize then, our superposition state between two energy eigenstates is going to be something that has an oscillating time-dependent electric dipole moment. It's going to be written in this form, where now we have three parts to it. We have this spatial, this coefficient term here. We have the transition dipole moment, which comes from just the spatial part of the wave functions. And then we have the time dependence due to the differences in their energies. So this omega is the light frequency that's given off, and that's the difference in the energies divided by h bar. The coefficients give us the time scale of that transition, and this integral here, this transition dipole moment, tells us the magnitude of that dipole oscillation. Now, this is, again, something we're going to come back to more in this chapter and in the rest of the class. And this is a dipole moment vector, so we could calculate the expectation value for the components, the x, y, and z component, and then add those components up squared, and we can get the total magnitude squared of that electric dipole moment, transition dipole moment. Okay, so that's it for this. We've shown that a system that's in a superposition of energy eigenstates has the ability to have an oscillating electric dipole moment and radiate light. So everything looks great now, in the sense that we have Rutherford's model of the atom allowing the electrons to be in an orbit and be stable and not radiate away their light. And at the same time, we see that there's a possibility for atoms to emit and absorb light once they get into these superposition of eigenstates. But it does raise another question, which is, okay, we know that they have to be in a superposition of energy eigenstates to emit light, but if it's in one of those excited energy eigenstates, how does it get into the superposition state to begin with, right, to start this? And the answer is that something has to sort of push it into that energy eigenstate, and that's what we're going to look at in the next lecture.